Can you see my presentation?
Yes.
Okay, let me go into full screen mode.
And I would introduce you so I don't make the mistake
go ahead.
with Remo. Berndt is a very close friend. We studied together physics in Frankfurt some very long time ago, wrote some very influential papers together. And Berndt is today also an ALS, which means laboratory director of responsibility for particle and nuclear physics and Brookhaven. I was thinking when I heard that of his interest in the statistics of COVID, but he must be
how is everything?
I will have to now mute Remo.
Beautiful.
Here we go. Did I mute? Yeah, I think I muted him. So Berndt is probably, I might guess, looking at the lab and asking himself a question: can he open it? And so this is. So I was really delighted that he chose to give us some insight about his thinking. Berndt, please proceed.
Well, thank you. Before I start, let me just make a remark on what I just heard. As many of you know, there is the saying that science is 90% perspiration and 10% inspiration. But there's one important thing missing, and that is serendipity. Inspiration and perspiration alone don't let you really succeed, but you also have to be have a certain amount of serendipity. And so in the context of COVID-19, as Jan, at least he knows some of this, I was very fortunate that at the beginning of the year, I had two doctors that I visited. One recommended BCG therapy, which I'm doing, and hopefully it helps. And secondly, my other doctor recommended that I take larger doses of vitamin D. So this was at a time when nobody took the serious, the coronavirus serious in the US. And so I count myself somewhat lucky. So let me now come to the slides. The first two slides actually a recapitulation of what really Giorgio talked about, namely the dynamics, the epidemiology of infectious diseases. And basically, there is a very simple transmission model that says that if you have a certain number of infected people, then the infection increases exponentially with a certain rate that's here denoted by little r. It's usually related to a capital R0, which is really the exponential of that little rate times a time that the infected people have to transmit the disease to others. So that is the time in which they are really infectious. And so, for example, if tau, this transmission time is of the order of 5 days, which may be roughly right, and little r is about 0.2, then R0 is 2.7, E, Euler's number, right? So if tau is 5 days and little r is minus 0.06, then R0 is about 3/4. I mentioned this because you will see these numbers come up in my analysis. Of course, there are many more, much more sophisticated transmission models that Giorgio mentioned that take into account latent infectious periods, the isolation of symptomatic people, and so forth. And generally, they're known as SEIR models. They, as George also said, they distinguish really 4 population segments. One is the susceptible population, that is the population that isn't immune, the exposed population, the population that's already infectious or still infectious, and the people who are recovered. And usually in these models are assumed to be immune. These models are then usually described by differential equations, although there have been arguments that these have to be more general equations. For example, in the work by Fodor and company, they are integral differential equations because they take into account memory times and so forth. So that's the basic epidemiology. What I wanted to do is apply the simplest description that I could think of. And from what I saw about a little over a month ago, was that obviously we have a situation that's what Giorgio calls the natural situation, in which the disease basically runs unimpeded, unmitigated. And we have situations in which society takes certain precautions against transmission of the infection. So I distinguish two periods. Period 1 covers the uncontrolled epidemic, and period 2 covers the controlled epidemic. For example, by stay-at-home orders, or just by spontaneous public response to the presence of the epidemic, and people are less congregating or less interacting. So I wrote down a formula that interpolates between these two periods, the simplest formula I could think of, where I have an exponential that describes the first period with as a function of time from a start time where one counts, and then a second period that has then falls off exponentially with little r2. And when you write this in a formula that has the right asymptotic limits, the one that I wrote down for n of t just works. It turns out that quite a few countries actually have superimposed on these trends weekly modulations. And they're probably simply due to reporting of positive cases. And so what I said is, let's modulate this with a sine function with an undetermined period, which we'll find out typically is about 7 days. That's why it's supposed to be weekly. So that's all that goes into what I talk now. Very simple, the simplest possible model. It does not assume any causal relationships and so forth. It just tries to see how can we describe the data in terms of very few parameters. In the simplest model is 4 parameters. In the more sophisticated, with the modulations, it's 7. So now let me show you the results. As Jan said, I was originally interested in Brookhaven. What's the situation of the surrounding county, Suffolk County? And what I found was initially that the growth of cases of staff in Brookhaven and the growth of cases of Suffolk County ran completely parallel. In other words, the ratio just stayed constant for at least a month. And so really it mattered what happened in the surrounding county, which is Suffolk County. And so this shows now the statistics of confirmed cases of COVID-19 in days starting from March 1st. And you can see on the left plot that it initially rises steeply, then it goes into an S-shaped curve. And with the fit that I show on the right-hand slide, which now shows the new daily cases, not the total number of cases, what you find is that it extrapolates to about 40,000 cases in a population of roughly 1.5 million. You see that the 4-parameter model actually works very nicely. There are quite a bit of fluctuations of daily reporting around these curves, but what you find is that the parameters are R0 is 0.2, R1 is 0.2, corresponding to an R0 of roughly 2.7 in the unmitigated state, and now of an R2 that's close to minus 0.06. So there is a huge peak, but then it's falling off. What you might want to remember is that this is for a population of 1.5 million. And so for the other regions that I am looking at, I have normalized it on the same number on the same size of the population. So I've divided the population of the region, the country, by the appropriate number so that it's normalized to 1.5 million. Okay, so we see a fall off, and now you can ask the question, well, yeah, if you have points like this, data points, you can fit it with 4 parameters. But the remarkable thing in the next slide is that I had virtually these parameters already identified on April 20. So the left plot is the one that I just showed. The right plot is showing in black the data points that existed around the 20th of April, a month ago. And the curve shown there is the 4-parameter fit to these data points. The parameters are virtually unchanged from those that the fit today gives. It extrapolates to the same total number. The difference is that the error bars are considerably larger. With the exception of really one data point, red data point, all the data points that we have acquired in the last month actually fall within the 90% error bands. So that was quite surprising because I was thinking that maybe quite a bit would have changed over the past month in terms of social dynamics. But I think what this really shows is the social dynamics of suppression once it was well, both approved and recommended, you could say almost dictated by the authorities, was extraordinarily stable and is still stable now. So you can compare this with Germany. And when you look at Germany, you see that the parameters are almost identical. It's a natural period in which the infection runs nearly unconstrained, and then a rigorous control by the population that stay-at-home orders, social separation orders that are very effective in cutting down on the number of new infections. In Germany, what you see is this modulation, and I've used here the 7-parameter fit, and what you see is that, yes, it's indeed a week. Actually, the fit gives you 6.9 days, but it's in terms of the prediction of the total number of cases at the end and so forth, it really is the same as the 4-parameter fit, except it describes the modulations very nicely. Here I've normalized by 55, a factor 55 to account for the population of Germany, which is 83. What you see also is that when we go back to this slide, the peak in Suffolk County is at about 1,200 new infections per day. The peak in Germany is a little over 100. And so there is a factor of more than 10 between the Newark area and Germany as a whole in terms of the infection, in terms of pandemic.
I mean, Germany as a whole, in the sense, not renormalized by population. So it's
correct, right. And you can ask the question, why is that so? And I will tell you later what explains this? Let's look at Italy. Again, we get a nice fit with the natural R1 of 0.2. Describes the data very nicely. On the right-hand side, you see again, it's a nice weekly modulation. However, what you find is that the R2, that is the rate in the mitigated, in the controlled state, is not minus 0.06, but it's minus 0.033. And of course, that has a tremendous effect on the total number of cases. And it leads to a much longer extent and duration of the epidemic in Italy. I don't know why that is the case. It could be that the social conditions are different, but that's certainly what it shows. What you also see here is that the last 2 weeks or so, the data points systematically fall below the curve, below the model, which suggests that there is actually a tightening of the control mechanism of the epidemic in Italy happening right now. And so one could imagine fitting it with, instead of 2 periods, with 3 periods. I've not tried that, but there is a suggestion that actually Italy is performing better than the simple global fit at this point. North Carolina. I'm concerned about North Carolina because that's where I am. Duke University is in North Carolina. And what you find is that actually the overall rates in North Carolina have been much less. Again, it's normalized to the population, but you see we were initially much, much lower than the numbers in Suffolk County or in Germany or in Italy. However, in this case, we are now in a period where the epidemic is somewhat controlled, but the rate in that control is still positive. And it has been positive for a month. It has not budged. And when you go outside, you find most people outside don't wear masks. And so my interpretation in the end is that this is due to the fact that the control mechanisms and the control orders were instituted, relatively speaking, at a much earlier time, relative to the onset and the dynamics of the epidemic. People never saw the peak. Most people don't know anybody who's got it. Whereas in New York, most people know somebody who actually has been affected. And some people even know others who were in the hospital or died. In North Carolina, that never happened. People are less afraid. And so even with stay-at-home orders of the governor, the infection is not controlled in a similar way as it is in New York area or Italy or Germany. United States as a whole, of course, here we're dealing with regions like North Carolina, like New York, like the West Coast, like the Midwest, that are extraordinarily diverse. And so fitting this with with 4 parameters in a region, in a country as large and diverse as the US sounds almost crazy. However, you find that actually it works extremely well. You have to put in the weekly modulation on the right-hand plot, and you can make a prediction. Unless something really changes, there will be about, it extrapolates to 3.6 million cases in the US overall. But whether that will actually be the case when now reopening happens is something we'll see. And the fall off is a lot slower. The natural rise is not much different from elsewhere, but the fall off is now quite slow. So, a few just model analysis. I looked here at the cases of Suffolk County. That's the red curve is the actual. And I asked myself, what would have happened if the stay-at-home order with the rigorous control and mitigation of the epidemic had been issued either a week earlier or a week later? And the week later is the blue curve, the blue dash curve. The week earlier is the red dash curve. It's the green dash curve. So you see there are tremendous impacts of just 1 week of delay or not delay, or acceleration of these measures. And the total number of infections under these curves differs by a factor of 4. So it's just 1 week that makes a huge difference. And so what you can also do is you can ask the question, why is there a difference so much between Germany and New York? Well, here you have the answer. If you take Suffolk County, which is essentially identical to the New York metropolitan area, and you say, what would have happened if the stay-at-home order had been issued 12 days earlier? When people were beginning to say, we need to do this, the experts were clearly saying that, but the politicians were wavering. They didn't have the courage to actually give the order. And so with 12 days earlier, the Suffolk County curve would have looked almost identical to the German curve. So the success in Germany, in my view, is mainly that the politicians have acted earlier, and labs and shops and public life was closed down a little more than 2 weeks, a little less than 2 weeks earlier. We had discussions like this at Brookhaven. We obviously could have done it, but in the national lab, you also have to wait for politicians and federal governments to agree to do this. And that's what really, in my view, had that effect. We're coming closer to the end. I'm now comparing North Carolina and Suffolk County. In the case of Suffolk County, you see that huge peak and now the tight control. People are really scared. They're staying at home. They wear masks when they go out. In North Carolina, there is not that systematic reaction. And although the infection rate here up to now was much, much less than in the New York area, you see we're approaching the point where actually the relative number of new cases, of new infections in North Carolina will begin to exceed those in Suffolk County in the New York metropolitan area, simply because people are not reacting responsibly. And so one has to begin to think about, should one go back to New York? So the governor's office has made a plan of how to reopen and so forth. And there's an interesting graphics in there, which I could have done using the model that I've used, but they did it. And they asked the question, if they open again on June 1st, and if the R value, they call it RT instead of R0, but I mean, it doesn't really matter, no longer stays at 0.75 as it is now, but it grows back above 1, what are the consequences? And you see that the consequences beginning in July and then August would be drastic in terms of a second wave of infections coming. Okay, finally, it's time to say happy birthday. Jan, I was looking for a picture that showed you drinking with me, and I found this nice one from a previous birthday party, and a place that you, I'm sure, remember very well. So happy birthday, and I hope we will have a similar picture next year.
It's wonderful, Berndt. This is a really nice find. I forgot about this picture. I have it someplace. Thank you very much for the very nice presentation. Above lots of substance in it. And so I have a question immediately to you. So you basically, if I look at the prediction in looking into the future, how would you evaluate what is now going on in the United States and in the world? Basically, ready for a second wave, or is there a chance it will not come? Ready for a second wave, or is there a chance it will not come?
We have an echo. I don't know who causes it.
Giorgio came on, and Giorgio has a problem. He has to mute. I have to mute Giorgio. Or he muted himself, so it's good. Okay.
So,
I muted GGB. I don't know who it is, but GGB was doing vacuum.
okay. So, I mean, of course, I don't have a crystal ball. However, I can make a guess. I think what Italy, Germany, New York area have shown is that when people see the runaway infection, they get scared and they're willing to isolate, and they're willing to take precautions. It's clear that the rigorous precautions with stay-at-home orders are not sustainable. And so one can expect that the effective R0 will increase. But I think in those areas, it will probably be possible to keep them not far away from 1. I think what North Carolina shows, as many other areas in the US that are, how should I say, they were not initially deeply affected, is that the population does not really generally see the need to be rigorous in preventing infections. And so it seems to me very unlikely that it will be possible to keep the rate at 1 or even below 1 in those areas. That's very large parts of the US, including North Carolina. And so I would expect that we'll see a slowly growing epidemic over the summer that will not go away. Now, I don't want to, judge here whether that's the preferred or not the preferred mode in which one deals with this, but that would be my expectation, that overall people will get more lax. The regions that saw the first big onset will remain very cautious, but the rest will see infection rates that have a low exponential rise into through the summer and into the fall.
I have, on this context, a small side question. Germany and New York, Suffolk County, in terms of vitamin D, are very similar, I would imagine, although I don't have the data. Could you look at your parameters? I mean, they are very, there's Australia, there's Austria, there's Norway. They are all, past their peak, and you can easily fit their data and see how the parameters which you defined, how these depend on country characteristics, for example, vitamin D.
I mean, I could if I had the time or a student or a postdoc, which I don't. But I think maybe this encourages or suggests somebody who wants to do that. It's not hard, but you need a little bit of time in applying it to many more countries.
Yeah. So I know that Giorgio is waiting to ask a question. I'm unmuting him. We must be prepared for a little bit of acoustics.
Sorry, yeah. I wrote it in chat, but here's the main thing. That in the press, one of the things that was emphasized was to flatten the curve, which is this in this concept, the disease spreads slower, but unless the government builds in additional measures, the area under the curve remains the same. In your models, in your fits, at least intuitively, the area under the curve changes a lot as well, right?
Oh yeah.
Just to understand what is happening.
Oh yeah.
Be,
Oh yeah. So
the total
let's
number of
see
infections.
here. Yes.
Yeah.
Oh yeah. So let's see here. Yes. Absolutely. However, that means that one has the control such that the asymptotic R0 in the controlled phase is below 1, right? If it is larger than 1, then you can't, integrate to infinity. And I think if you keep the R0 at 1 or slightly above 1, then eventually everybody will be infected until you have immunity, sufficient herd immunity. So you can call that a flattening the curve. This is more than flattening the curve. This is really bringing it drastically down at large economic cost.
That was the word cost appeared for the first time today, which is good because we are, of course, not into economics and politics, but into science. I think ultimately your model is really brilliant, Berndt, and ultimately the issue which is in front of us is to get these parameters which you introduce with success, obviously, to be dependent on factors which are visible, because you see, the one thing is even small changes in the parameters have a gigantic impact on the outcome. Quite as the one factor which you produce is when politicians decide to shut us, to allow us to stay at home, so to speak. But
right. So I think the two interesting questions in that context. One is what influences these parameters, right?
Yeah, that's exactly.
And I mean, of course, we know that conscious measures can influence them.
Yeah.
Right. But there is also, of course, the likelihood, great likelihood, that it is factors that are not conscious, but that are, given by nutrition, by circumstances, by medical preparation, smoking, that influence these factors, right? And we just don't know. Now, notice that I only looked at the number of reported cases, not about how many of these cases are serious, how many people are hospitalized, how many people die. That's an entirely different question.
So we'll talk to him soon, but other people are talking to him right now.